Okay, so welcome everybody for the afternoon session. It's our great pleasure to have Tadashi Takayanagi continuing with his Chandrasekhar lectures. And in this lecture, he's going to tell us about pseudo entropy and de Sitter holography. Tadashi, please take it away.
Thank you very much for introduction again. Also, thanks for invitation. So in this my third lecture, I'd like to talk about some new quantity which we call pseudo entropy, which is generalization of entanglement entropy, and its connection to holography in de space. So, but let me begin with a broad introduction. So this is about quantum. We want to generalize quantum entanglement, but let us in mind what was the quantum entanglement. So this is like you can imagine some Bell state. Then there are two spins A and B, and they are highly correlated in quantum mechanical matter. So we have A is up spins, and B is down spin, and they cancel each other always, and that means A and B, A spin and B spin are strongly correlated. And this Bell state gives us a minimum unit of entanglement. And especially for pure states, we can say non-zero quantum, there is non-zero quantum entanglement whenever a wave function is not factorized into direct product into A and B. So this is a basically definition of quantum entanglement. And the best measure of quantum entanglement is entanglement entropy, and that measures the effective number of these Bell pairs, which exist between A and B. And to measure entanglement, first thing to do is to use some entanglement entropy, especially in high energy literature and also condensed matter literature. For that, already mentioned, but it's a very simple thing. So we decompose Hilbert space A and B, and we trace out subsystem B. So we have an observer is sitting A, and so we trace out B. And we have some a density matrix for observer who are living in A. That is a reduced density matrix. And from that, von Neumann entropy minus trace rho log rho, this gives entanglement entropy. This is a very convenient definition of entanglements because we can calculate this quantity in many different ways, like, for example, replica method in quantum field theory or direct real space-time formalism. So in general, so we start with qubits, like so quantum many-mode systems. There are many spins, and we can just call this 9 spins are A spin, and other are B. But you can take a continuous limit so that lattice constant goes to 0, then we reach, roughly speaking, we reach this quantum field theory. So to calculate entanglement entropy, we need to specify just separation between A and B. So once we specify this, then we can define entanglement entropy. So this is a usual way to calculate entanglement entropy, but also I'd like to also emphasize more quantum information theoretical understanding of this entanglement entropy, which is also important in this talk. So this is about, this is called the resource theory, or more operational way to understand the entanglement. So our setup is like this. We have a spin here. We have many spins, but let's call this part is A spin and B spin. And in general, highly complicated way, they are entangled with each other. This spin is entangled with this guy, also at the same time this guy, and they're very complicated. So it's not easy to naively count number of Bell pairs. And in that case, we do the following operation. So this is a famous operation called LOCC. So LO means local operations. So let's imagine A and B are highly entangled, but they are quite separated laboratories. So inside the laboratory, we can make very highly sophisticated quantum operations. This is a LO. We can do some projection measurement, or as in the previous talk, and we can do some projection measurement or a unitary transformation independently A or B. But we cannot mix A and B in quantum mechanical way because they are far apart, so it's not so easy to do some sophisticated operation. But between A and B, we can also always send some classical information, like sending emails or making phone call and so on. So this is a classical communication. So this is quite also, very natural setup, which we can imagine. So if A and B are far apart. Of course, the basic example of this LOCC protocol is quantum teleportation, and we can, there are many applications in quantum techniques. But here we would like to use this LOCC to extract some number of Bell pairs. So initially, it's A and B are very highly non-trivially correlated, quantum entangled. And but we can act this LOCC to make the state simplify. A very simple state that just only we have a nice Bell pairs between. So we have two Bell pairs which bridges between A and B. So we can optimize this procedure. We can extract the maximum number of Bell pairs, which we can extract from LOCC procedure. But that's not enough. So to get a nice result, we have to take so-called asymptotic limit. So we have to take infinite many copy of original system and do this LOCC, and we get some nice number, maximum number, which we call n. But of course, we already take a m copy of original system, and m goes to infinity, so we have to take a ratio. If we want to just pick up one of the state and how many Bell pairs are there. So of course, number of Bell pairs are quantized integer, but because we are taking ratio, so this can be arbitrary number, real number, a positive number. So this the well-known fact in quantum information textbook is a very beautiful fact that this ratio in this asymptotic limit precisely same as this usual definition of entanglement and von Neumann entropy definition. This is a very basic fact, and because of that, we can think this von Neumann entropy as some measure of quantum entanglement.
Always a rational.
Absolutely, because we're taking m goes to infinity, so you can approach this irrational number. Okay, so in this talk, we will introduce a generalization of entanglement entropy, which we call pseudo entropy, and there are three motivations for this. First motivation, we want to generalize entanglement entropy so that it fits nicely with some post-selection process. In post-selection state process, we start with some quantum state psi1 and finally projected down to psi2. So there are two states, initial state and final state. Of course, entanglement entropy here, of course, it only depends on one state psi, but we want to generalize this quantity so that it depends on two different quantum states. And another motivation is more holography. So actually, this is our original motivation why we first came up with this idea, is we want to generalize holographic entanglement entropy to Euclidean time-dependent background. So we discussed static background, Lorentzian time-dependent background, we can use extremal surface formula. But what about a Euclidean time-dependent background? So but still we can define nice minimum area surface. This is second motivation. And the final motivation is we want to understand some holography of Dojita space, and then somehow inevitably we encounter this kind of generalized notion of entanglement entropy. So I want to go explain these points in this talk. Now the reasons why we need this quantity is dual CFT in DSCFT, as long as we stick to original DSCFT like original Strominger proposed, it looks like dual CFT looks like non-Hermitian, and this is somehow good entropy for non-Hermitian systems.
Tadashi, when you say non-Euclidean, Euclidean time-dependent background, do you mean backgrounds which break time reflection symmetry?
We don't require that. So it's an initial state and final state is different. And different. Inner product of two different states. So the main I'm going to also mention other works, but these are main differences. First one is with these people is about original paper where we propose this pseudo entropy and gives its gravity dual. And the second paper with Doi and Jonathan here, and Ari Morabashi and Yusuke Taki. And this is about application of the pseudo entropy in the case of DSCFT correspondence. And finally, I also, if I have time, I want to mention our latest work with Doi, Ogawa, Shinmyo. They are all our graduate students. This is about dual CFT states in DSCFT. But here, this is not involved with entropy, but this is where this non-Hermitian nature, which is important in pseudo entropy, also plays very important role. Okay, so here are contents. So first, I give some Euclidean time-dependent version of holographic entanglement entropy. That's we would like to discuss this, and then go to what is I will give some definition of pseudo entropy and the holographic counterpart. It's related to this one. And also, I talk about some quantum many-body system application, especially in the context of quantum phase transition. And then go to Dojita holography, and it's related to this pseudo entropy, and also recent work to some probe CFT, as a probe this one point in Dojita space by using CFT viewpoint. So this is okay. So let me start with this. What's the version 3 of holographic entanglement entropy means? This is a version 1. This is a static space-time. So this is, we just take a minimum surface because we can forget about time direction because it's static. And we can go further to reach this covariant formulation. And this is in time dependent, so we have to take into account full Lorentzian space-time. And in that case, we can just pick up extremal surface, which not minimal, but it's just extremalise the area functional. So we just calculate this area and then divide it by 4G Newton, and that gives So this is up to this is quite standard story, but now we'd like to mention this version 3 formula. This is about the minimum area surface in Euclidean time-dependent asymptotically area spaces. So we talk about the Lorentzian time-dependent. That is just quantum states are time-dependent, but in Euclidean time-dependent case, we have a Euclidean path integral, but initial state and final states are different. So this means that some post-selection procedure. The initial state psi1 is different from psi2 final state. And then the question is what kind of quantum information quantity in CFT is dual to this minimum area. So, but naively, one might think some entanglement, but this is not be true because there are two states are involved, psi and psi2. And the correct answer is this quantity which we call pseudo entropy. So what's the pseudo entropy? So let me give a definition. This is actually very simple. So the only non-trivial element is that we have two different states, psi and bar phi. Psi and bar. We put them into the transition matrix, Bura and Ket. So we put some psi and bar phi, and we just normalize by inner product because we want the trace of this guy to be 1. And this is what we call this transition matrix. And this is just reduced, this becomes usual density matrix if psi and bar phi are same. But this is not true in this setup. And so now we decompose Hilbert space HA times HB as usual. And then we introduce this reduced transition matrix, reduced version with tracing at B. But the point is that this guy is not a Hermitian. So it's going away from usual definition of entanglement entropy. But nevertheless, let's define the pseudo entropy is in terms of just tau log tau. This looks like von Neumann entropy, but tau is not Hermitian. So that's the reason we put some pseudo. It's not exactly usual entropy. And we can also easily to generalize the Rayleigh version. So this is quite useful to calculate this quantity in a replica trick. It's like this. You can take n goes to 1 limit basically leads to this formula. So now, let me list up some basic properties of this quantity. So in general, this reduced transition matrix is not Hermitian. So this quantity is complex valued in general. There is an imaginary part in general. But in a good case, like for example, if we have some Euclidean path integral with all real valued external sources, it's this standard with real value, and also simple holographic situation, even if there is a Euclidean time dependence, still the quantity is real value. But in general, it's complex valued. But in these special cases, we have a holographic case, and if we have a pseudo Hermitian property, and also in the case of entanglement transition, this is something I give a talk in the end of the second lecture. So somehow, this nice coincidence we get some real value, real and positive value. And the second thing is that if there are no, means that this quantity is related to entanglement definitely, because if either psi or bar phi has no entanglement at all, there are no correlation between A and B, then this quantity is always, for any n, pseudo entropy is 0. And if we flip initial state to final state, this you might easily guess from if we flip this, it looks like dagger conjugation. So entropy also conjugate. This means, of course, entropy is not in general complex value. And also SA equals B like in equality is also holds. So tracing out B and equal to tracing out. Because this is essentially same as this is sort of pure state. And if these two guys are same, of course, this reduced to standard linear entropy. So in this case, of course, we know much about it, so not so interesting in this from this viewpoint. And one comment is that actually this kind of unusual quantity appears in the context of also in the literature of this post selection. So you can often we can consider this kind of quantity. The OA is just Hermitian operator, usual physical variable, but the initial state and final state is different. Then it's natural to consider this expectation value. And this is, you can rewrite this in terms of transition matrix. And this quantity is not guaranteed to be real value, even if O is Hermitian, because it's exactly the same. But such a quantity is. Good question. If this is orthogonal to each other, we cannot define this quantity. So, yeah, I'm always assuming this overlap is not 0. Otherwise, this quantity is not well defined. So, but anyway, this quantity is called weak value in the context of quantum information theory. So it's a complex value, looks like difficult to measure, but you can individually measure real part and imaginary part in explicit some experiments. And Therefore, this pseudo entropy, you can regard this pseudo entropy in terms of this, in the language of weak value. You can think this is a weak value of modular operator. So it's like a modular Hamiltonian-like, but it's log of tau A. Tau A is a reduced transition matrix. And this quantity, so like analogous to this one. Yes? So OA to be, let's take OA as a Hermitian. But still, this is complex value in general. Okay, so so what's the meaning of this quantity? So in general, it's not so easy to make this, quantum information theoretical meaning of this quantity. But if we really restrict a particular class, this class E means this one, just both tau A and tau B are both Hermitian and semi-positive definite. So this is still general more general than usual.
Sorry, is HA in the previous slide is the modular operator or is the log of the modular operator? Is
log
the log?
Yeah, the log of this. Yeah, log of this transition matrix. Yeah, in the end, this operator turns out to be area operator in Euclidean time. And so let's focus on very simplified class. States are more wild, but let's talk about the simplest case where this tau A and tau B are both Hermitian, but they can be different, but there are some Hermitian has a nice same positive property. And remarkably, in this case, we can show a very nice interpretation, quantum information theoretical interpretation of this quantity. So this is in this case, this quantity is guaranteed to be real and non-negative. And so no imaginary part. And that case, we can actually interpret it as a number of distributable Bell pairs in the intermediate states between this psi and bar phi in the post-selection procedure. But here again, we take basically this derivation is basically same as what I mentioned about this well-known fact of LOCC. And yeah, I can just quickly mention this. And so for this case, simplest example of this case is we can always like this way. So psi and bar phi is this is 0 and 1 is a qubit state. It's a linear combination with some coefficient, but the coefficient is real value like this. But it can be psi and bar phi can be different because angle can be different. And then this reduced transition matrix take this form. We just trace out one of them. And then pseudo entropy takes this form. If theta 1 equals theta 2, this is well-known formula for usual entanglement entropy. But in general, theta 1 and theta 2 can be different. So in this case, what we can do is do the following thing. So we can take this original state psi and take m copy of that. And this is cosine theta 1, 0, 0. I write cosine theta 1 to be C1 and sine theta 1 is S1. And this linear combination. Of course, this angle is pi over 45 degrees, then it's a real maximally entangled Bell pair state, but in general, more generalized. The non-trivial ratio, and we take m copy of that. We take m copy of, and in the end we take m goes to infinity. But we can do binomial expansion, and there are there are 2 qubits, but times m, so there are 2 m qubits. So this m qubits here and m qubit here. Interestingly, they are of course they are highly correlated. This guy and this guy is same, so that means if k, let's take this is k equals 0, then this guy k equals 0 means 0, 0, 0, 0, 0. If we expand this, it's obviously 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0 is also here. Right? And then coefficient turns out to be this C1 to m's power, k equals 0. And the next order, so there are one piece coming here, and there are m minus one piece here. And then we have a 0, 0, 0, but all except the first one and other things are 0, or you can repeat other way. So this one can be in a second entry or third entry and so on. So it's like, anyway, we end up with this maximally entangled state with this coefficient. This is an important point. And then, so we can do this projection to this maximally. Once we get the maximally entangled state, it is very easy to estimate the entanglement entropy. So we want to do projection measurement. We can only act A, subsystem A. We don't need to breach A and B. It's just do some projection measurement for A to restrict the state to this one. And then we can measure some, we can also estimate its probability, it's the square of this coefficient. The probability is just given by this one. And there is this CMK is like this binomial coefficient. There are such a number of possibilities. And this is a probability distribution. And each k, you have one maximally entangled states appears. So k equals 0, not trivial, right? So there are only one state involved. There are entropy 0, but k equals 1, there is a k different state, m different states appear. So it's like entropy is log m. And that way, in general, you get the entropy log CMK, binomial coefficient, and with the probability distribution. And we sandwich, point that we sandwich the different states. In usual entanglement entropy case, we have the same state here, but we have a different states, and we sandwich because we are doing some post-selection. So then we take this average, then we can do this integral, we can rewrite this sum into integral about k, and m goes to infinity, then we get some sort of point approximation, which precisely reproduce this formula. So that way, this particular case, we can understand this meaning of this quantity. But in general, this quantity gets imaginary value, complex value. So precise understanding is still not available. But anyway, this quantity is very useful because when this quantity is real value, that appears in holography, and that seems to give a very basic geometrical quantity.
Excuse me,
Yes?
in this special case, when you said this tau A are positive and Hermitian, was it clear that this pseudo entropy is always bounded between 0 and 1?
0 and 1. This guy, okay. Yeah, in general, pseudo entropy is not bounded by anything, actually. But this special case, I think it's, okay, yeah, but sorry, not really, no bound here. Even this special case, there are no bound. Because you can see from this also expression.
Okay, so it seems...
This can be very, very large, right? It can be 0. Then it can be very, very large.
More entangled pairs than you actually have?
Yeah. So that case is, yeah, that is, because the reason how that happens is because we have a denominator. This can be very small, right? If bar phi and psi are very small. That can actually, enhances the result. So that doesn't contradict with this one. Because we define this extracting procedure like this way. But the quantity is positive. Quantity is positive, yeah. But but this is somehow looks, at first it's very strange. So maybe it is interesting to ask whether maybe we can improve this kind of quantity. This is actually something we worked out recently. This is what we call the SBD entropy. In this case, it's manifestly positive, and it's bounded by just number of Bell pairs, original Bell pairs. So this is just instead of tau A, but also we take a square root, absolute variable tau A, transition matrix, and just compute this tau log tau. So this is quite well defined and quite well behaved. And you can also, in this case, we can have any choice of initial state, final state. We can say that. So this quantity is like essentially picking up number of pairs between this initial state to final state, but we act some unitary transformation, so optimize number of imperial pairs we extract somehow. So the whole special U and B, which is defined by this singular value decomposition. This is in general, it's not a Hermitian matrix. We take some U and B unitary matrix to diagonalize it. We need two different unitary matrix to diagonal this non-Hermitian matrix, and using that basis, then we can say precisely this quantity measures amount of Bell pairs.
Losing track of the notation a little bit. Here tau A is always defined as the modular operator, right? The transition matrix for the modular operator.
Transition operator.
For the modular operator.
Tau A more precisely. This one. Okay, good. Yeah. But this quantity is, looks good, but actually not so easy to calculate because of square root and so on. And there are so far we don't have any good understanding of this quantity in terms of holography. So I'm not going to talk about it. For example, SA is not equal to SB in this quantity. It's interesting. But still we can see this quantity shares a very similar property as pseudo entropy that we will explain later, about the phase transition of quantum manifold systems. This quantity has a similar behavior. So, but now okay. So I go to this holographic calculation. It's already mentioned, advertised, but so we are interested in this Euclidean time-dependent background, Euclidean time-dependent asymptotical radius background. But in that case, this asymptotical radius, we can define minimum area surface, gamma A. This is quite well-defined object. And what's the meaning of that? And it turns out this is exactly same as this pseudo entropy. And if this density matrix is pure, then it's obvious. Everything is covered so that this gamma A becomes trivial, so it's just 0. And if we psi above phi is not entangled, this also quantity is there because we put some end was boundary just here. That means this state is not entangled. So then if there is end was boundary, this minimal surface end on the.
Here, psi and phi are the states in the bottom and the top.
Yes. Yeah. Sorry. Yeah.
I see. But the A is marked in the middle. So I'm confused. Psi is defined as.
Psi is, we do this path integral and define psi status here.
I see. And phi is defined at the bottom. Or at the top.
The other side, yeah. So this path integral from infinity to this point define psi.
Oh, I see.
Yeah.
Infinity to this point defines psi. And whereas phi is on the other side.
Sorry.
And
phi is the other side.
Phi is the other side.
This side of this is a phi and this is above phi.
And is it clear that the surface, the minimal extremal surface, lies on some particular, like, it's not like there is time reflection symmetry in this background, right?
Yeah, no.
So you just look for some
extremal. This
extremal.
is an inner product. This is basically if we pass integral everything, it's like inner product.
Right. So the surface is some extremal surface which
this is a minimal area surface. Minimal area because everything is Euclidean.
Okay.
So this is quite well defined minimum area surface.
I see. But it doesn't necessarily lie on any particular Cauchy slice because there's no time.
No. Yeah, good thing. Yeah, this is not on any Cauchy slice. Yeah. In general, it's very complicated.
And you can have operator insertions both on the top and below to define psi and phi, I suppose.
You can put some operators.
Some operators.
Yeah, you get that.
And the fact that this minimal surface might go all in one direction or the other direction as one colors, that doesn't matter. For instance, the minimal surface might go purely in the direction of in the top or in the bottom. So it looks very asymmetric somehow.
You mean, sorry, this surface, gamma A?
This surface, right?
Yeah, this can be upward or downward.
Okay.
Because these two states are not same. So
Okay.
That breaks.
Okay.
Yes. Transition matrix determinant, why? I don't think so. Okay. But anyway, it's not, we cannot define it because it's like not exactly always rectangular. Not square matrix. It's like Hilbert space can be, dimension can be. Okay. Yeah. Good point. I think it's not degenerate. Yeah, but in general, this is not degenerate. Because that's the reason, indeed, this entropy is not there. But if there is a such case, very, unusual case where this rank of this transition matrix is less than maximum rank, then we get some funny result. But this case is, I think, so don't have any such a problem. And also, SA equals SB is obvious from this picture. B is just the other side, and always this is a surface. So one might ask us what about strong subjectivity, but strong subjectivity is not a good question actually. So these are Euclidean times, so not the Lorentzian times, so there are no causal, Cauchy slice and so on. And you can easily violate something naive strong subjectivity by choosing this kind of wavy surface. So I'm not going to talk about it. But the derivation of this holographic Pseudo entropy, this itself is basically the same as what Lukoitz and Maldacena did. So as just mentioned by Subrat, so we can put some operator. And if these two operators are different, then define, of course, different quantum states. And we take a multiple copy to compute this replica method. This is defined, this path integral is psi, and this is above phi. And we just path integral over all n seeds, and then we get this partition function, which is basically computes this nth linear entropy, but nth Pseudo entropy. So this is a holographic calculation, so we can find many examples where we can analytically compute this. But let me go to some other applications, so especially application to quantum measurable systems. So how much this quantity can capture some interesting feature of quantum phases. So first of all, these are basic properties in quantum measurable system. We can talk about this basic property of Pseudo entropy. So first of all, it satisfies area law, like this. This is the same as entanglement entropy. And the difference, we can talk about difference, and this is actually interesting quantity we would like to focus on. And this is like, so we talk about two different states, psi1 and psi2. And this is, the Pseudo entropy for that. And this is this is like 2-1, this is my mistake, 2-1, that means complex conjugate of this guy. So that means this quantity is always real value, even if this Pseudo entropy is not real value. And this is just a standard entanglement entropy. This means how much Pseudo entropy is enhanced compared with entanglement entropy. And interestingly, we can see that always this quantity is negative. if we work in a quantum field theory, in assuming same phase, that means we can start with, for example, free scalar, but just changes mass, essentially same quantum phase. And that case, always delta S is non-positive. So phi 1 is a ground state for mass m equal 1. Sorry, mass equal m equal 1. For example, this mass equal m equal 2. They different mass, but their ground state of Hamiltonian with different mass. This difference is always negative, like this. It's only 0 when mass parameter is exactly the same. But is this true in general? So what happens if they belongs to different quantum phases? So can this delta S be positive? And we can check this in some, there are many other also model we can try, we tried also. The simplest model, a quantum Ising model. So we have some interaction, this nearest neighbor interaction and with transverse magnetic fields. And we know this, let's take H equal 1, then J equal 1. When these two guys are the same, then there is a quantum phase transition. For large J equals to a ferromagnetic phase, but for small J, this guy is very important, so that means paramagnetic phases. So actually, if we talk about Pseudo entropy, which bridges two different quantum phases, this difference can be actually enhances to 0, more than gets larger than 0. So this is, you can see this explicitly. So if we look at this, then we set J1 equal 1/2, so 1 is a paramagnetic phase, but if J2 greater than 1, so as you can see, this blue guy is a Pseudo entropy is larger than average entanglement entropy. So this kind of phenomena happens when we have some two different quantum phases. So we have some kind of simple interpretation of this. So here is this interpretation. So this is psi1. Let's think some psi1 is some gap to phase, and psi2 also another gap to phase. But they are separated by gapless phase. So more typically, maybe if we think of some topological order, this is one topological order and other topological order, then there is a gapless mode localized here. But in this model, it's less topological. That means this is just Ising model, transverse Ising model. But still, we know at this point we have a critical point. So we change magnetic field. So that case, what we do is to calculate some sort of entanglement entropy, where subsystem is really localized at this interface. We put some subsystem A here. And if we imagine some gravity dual description, this is a gap to phase. So it's like ADS Soiton, like gap to ADS. But only here, there is a gapless mode. It's some real anti-Doshita space opens up. It's like Poincare patch appears. Here it's like global ADS confining situation, but it's like observed. So if we calculate entanglement entropy where minimal surface end of these 2 points, then this area, it's really enhances. If we calculate entanglement entropy for this region, it's like just doesn't grow so much. It's coupled, but this case is grows. So that's the reason actually Pseudo entropy enhances only when these two different states are in a different quantum phases. So, and also that motivates us also study some topological version of Pseudo entropy, which I did with Nishioka and Taki a few years ago. Also recently there are interesting paper by Pavel Kaptan and collaborator, just 1 week ago or so. So this might be somehow useful to understand this topological nature or some different quantum phases in quantum manifold systems. Okay, so now I talked about basically overview of how this Pseudo entropy looks like and what's the definition of Pseudo entropy and how this holographic calculation looks like. And then I'd like to talk about this holography means, but in the context of ADS CFT correspondence. And we see some, mainly I'm talking about the case where Pseudo entropy looks like real value. But I'd like to also talk about the case where Pseudo entropy can have an imaginary part and how it is useful in holography. That's this next.
Pseudo entropy have a similar relation to the pseudo entropy as topological entanglement entropy has to the entanglement entropy.
Thank you very much. Yeah. So yeah, actually, so in special case, this topological Pseudo entropy is same as topological entanglement entropy, but in general, the initial state and the final states are different. So it is more general quantity. And indeed, it's take a quite little bit different form that this topological Pseudo entropy also have an imaginary contribution. And so it's some parts looks actually completely different. But if, of course, two say the same, of course, it's just, and the simple case, just sum of two different topological entropy. But in general, this turns out to be quite different. That's interesting. And also, we can define something called, actually, this is also discussed, I think, Pavel Kapta's paper, the topological SVD entropy. SVD entropy we introduced. That is essentially the same as topological entanglement. So, but this guy has a special feature, and this has an imaginary part. Okay. So now let me go. So I'd like to talk about DS holography, application to DS holography. So in ADS-CFT, so we can talk about minimal surface and so on. It's like always real value. But in DS space, digital space, this is no longer true. And so anyway, but in ADS-CFT case, holographic entanglement entropy suggests that, so we might understand this extra dimension as some quantum entanglement, which come from quantum entanglement. So space-like direction may emerge from quantum entanglement. However, of course, our universe, phenomenological interest is a little bit different. We are more interested in digital space rather than anti-digital space. And then it's quite natural to talk about what's the holographic dual of digital space. So if we can think we can understand some nature of holography in digital space, it is quite natural to ask the following question. So can this digital space emerge from some sort of quantum information? So to understand this better, so let's consider first holographic entanglement calculation in digital space. So, but before that, I'd like to first give some very brief survey, review of DS holography. So this is a sketch of DS-CFT. So this first proposed by Ramanujan and developed by many people. So there are, of course, there are many different versions of gravity dual of digital space, gravity in digital space. But I would like to focus on more original one proposed by Ramanujan, and also in the formulated in Marda Sena's paper. So this is like this. So we have some digital space. So we can imagine some Hartle-Hawking vacuum. So we start with semi-sphere like this. And sorry, I'm mainly focusing on DS3, but here it's more general. So we have a semi-sphere, and a tunneling effect creates the universe, and then go to Lorentzian time evolution of digital space. And in the end, we reach to T goes to infinity. And usually holography tells us that Baruch spacetime is dual to boundary, and boundary in digital space case, we have a space-like boundary and future infinity, T goes to infinity. So this DS-CFT claims that, so this Lorentzian digital space-time, let's assume some Hartle-Hawking prescription. And that case, that this Lorentzian digital space is dual to Euclidean d-dimensional conformal field theory, which lives on the boundary of this space-time. It's a space-like boundary, so it's like a sphere, d-dimensional sphere. Total d plus 1 dimensional digital space, boundary is d-dimensional sphere. So it's dual theory should be Euclidean. So Euclidean d-dimensional conformal field theory. And then we can see the symmetry of CFT agree with classical geometrical symmetry of digital space, as is true in usual case of this ADS-CFT correspondence. And if we talk about physical quantity, so we can talk about CFT partition function here is essentially same as gravity partition function. In this case, especially, it gives a wave function of universe. We pass integral up to this boundary, it's a future infinity. And the important point is that in this picture, so we have a Euclidean CFT, but the time direction is extra dimension. Somehow time direction should emerge from this picture. That makes, of course, understanding this DS-CFT is very different. And then we'd like to discuss what we expect for this DS-CFT. So let's assume, but let me focus on the case where a space-time is very large. Like that means we can apply semi-classical gravity description, classical gravity description, so that we can apply just DS Einstein gravity. Einstein gravity is a positive cosmological constant. And then, so we start with d plus 1 dimensional digital space metric, but it is quite useful to go to Euclidean signature, as we often do with rotation. So t goes to it theta, and then we get this one. We go this way. This is just sphere. And then, but we can actually relate this space-time with anti-digital space. This is, of course, the usual anti-digital space. Euclidean ADS, it's like hyperbolic space. So this is easy to relate because we can ADS radius, L is LADS is ADS radius is imaginary times LADS radius. And also rho is I theta. Then this is mapped to this one. So that is but I mean very simple relation, but this gives many confusing feature that many eyes appears. For example, if we talk about central charge, which is very basic degree of freedom, if we talk about gravity dual, CFT dual. So in ADS case, we know this basically this ratio, ADS radius times some power divided by Newton constant. But this, because the radius becomes imaginary for ds, so we need this I to the d-1 factor, and some good ratio appears. And so if we talk about d is odd, then this is, I mean, real value may be okay, but if d is even, like especially we are interested in ds3 case, this I remains. So d equal 2 is a three-dimensional Dojita space we are interested in, then I factor remains. So it looks like for d even, so central charge seems to be imaginary value. And so also we want to take this central charge to be very large because we are interested in a classical gravity limit. So this is I mean, very simple survey which we can make if we assume there is a gravity dual to Einstein gravity of Dojita space. Okay, so now I'd like to go to some explicit, yes?
We can also derive this directly from the bulk. You know, if you just impose the Wheeler-DeWitt equation on the wave function of the universe, you'll find that it obeys some anomaly equation, which it has to have the form of ZCFT times a phase. And then there's an anomaly equation which will give you the imaginary central charge. So even without doing an analytic continuation.
Yeah, there are many ways to derive this, yeah. Anyway, it's related to anomaly. So if we have effective action, so then we can always read off central charge. So this is already discussed in this Marder sentence. So okay, so now I'd like to go to some further. So that means can we really have this imaginary central charge in d-dimensional case? So the d-even case. So this is a question, first question. So is it possible to find such example? Actually, we can find one by some analytical continuation. This is my works with Hikida and Nishioka and Taki a few years ago. Actually, we can see that in one such a example is given by large central charge limit of SU2 level K Witten model. But this details of the model is not so important. Actually, we can pick up some effective model like Liouville CFT, as I will explain. But anyway, so large central charge limit of some SU2 Witten model is actually turns out to be equivalent to Einstein gravity on three-dimensional Dojita space with real valued radius. So what this K means and what this large C limit means. So we have to take some analytical continuation about the level. So level K usually integer quantized into integer and positive integer or integrable representation. But we forget about the integrable representation. We are going to more non-rational CFT version. And there are many works also by mathematicians for such a non-rational version. So we take a level K to be -2 because we know central charge of SU2 based model is this very famous formula. K -2 gets divergent. But we have a next order contribution, of course, to regulate it. So that turns out to be Newton constant divided by ds radius times I also appears here. This is I is very important. And then the central charge obviously becomes the imaginary value. And this part looks like Brown N of central charge. So this basically agree with this expectation. So in that case, actually, assuming this relation, we can actually evaluate partition function of Witten model. This is actually, you can evaluate by using some equivalent Liouville theory description, but we can also evaluate it by mapping it to Chan-Simon theory, like description by Jones polynomial paper of the famous paper by Witten. So we can evaluate the partition function on sphere. So this is a model on sphere. And we can also insert, if you like, some Wilson loop operator. That corresponds to some insertion primary operator in the CFT side with some excitation. This turns out to be, this is quite a well-known fact, but turns out to be S matrix, modular S matrix of Witten model. And then we can relate this J is some excitation related to energy. So then it turns out to be precisely this, we produce Dojita space entropy. So exponential of Dojita entropy is also same as partition function in Dojita space. You can evaluate Einstein-Hilbert action, and you get the same result. So E is the excitation energy. And if we set the E equals 0, no insertion, that is exactly, we get the Dojita entropy. So this, if we take this limit, so we have continuation, we get a full Dojita space gravity. So also let me also I can mention that this k equal -2 limit looks funny, but actually it's equivalent to k goes to infinity limit. This is a semi-classical limit if we use this triarity relation by Gabadier and Gopakma in the context of this higher spin holography. So and continue to from ADS to DS. So this is -2, this itself is not so surprising. Also, we can SU2 model, but we are interested in the limit, this limit, so in the large central charge limit. In that case, leading contribution comes from Liouville sector model. This West minority model actually includes some Liouville theory. And Liouville theory is non-rational. We can take it's not rational theory and a more proper way to describe this unusual limit.
Formula. So this is the partition function of the theory. And what is E on the right-hand side? I didn't understand.
So this one?
Yes.
So we know expression of this S matrix, West2 West minority model in terms of J and so on, and level K. And we can just plug this value. And then we get this equation. Sorry, I omit many details here. So it's a conformal dimension of operator is related to energy, but again, we have I here. The energy of this energy is this energy. And so this S matrix, it's like little into a sine K of something. So maybe there's this kind of factor appears, sine, maybe K, for example, like this kind of factor appears. But we take this is K plus 2 is like I epsilon. So it's like C sine pi I epsilon, and which is like Shinchi. And this we can exponentiate it basically. And this basically gives this factor.
But maybe he's asking the J is related to delta.
Yes.
J to J plus 1 by K plus 2, the Zumino, that's how the you were
this is
about the E comes from the J.
Yes, E comes from the J. So and the essential part of this CFT actually governed by Liouville CFT. And so Liouville CFT actually, it's also this is an unusual Liouville CFT because central charge to be I times infinity, I times very large number. So if you're familiar with Liouville theory, it's characterized by some parameter called B, which appears in like this way, del phi square, and Liouville potential takes 2B phi, and there is some background charge term. Q is B plus. These are usual. Other papers, this normalization. So this B, actually B square turns out to be imaginary. So this is, we can find this result from here directly because we can match the central charge. Central charge is given by 1 plus 6Q square, and Q is given by this. And this, so we get some unusual Liouville theory. This is nothing like usual Liouville theory, or not like time-like Liouville theory, which appears in the context of tachyon condensation.
Is it related to this other recent Liouville square?
Yes, exactly. That's what, I wanted to. Thank you. Exactly. So actually this, as Rajesh mentioned, so this unusual Liouville CFT, because we have two Liouville theory here because we are talking about this square. That means we have a sphere. We have some Hartree-Hawking prescription creates one semi-sphere gives quantum state and the other quantum state is here, and we take an overlap. So this double copy appears. But actually, recently, interestingly, so Berlinde and Jan actually encounter same CFT and in the context of a double scaled S by K. So double scaled S by K is conjectured to be also dual to Dojita space. It's but not DS3, but DS2, I think. But maybe we can dimensionally reduce from DS3 to DS2. But that analysis of double scale S by K also leads to same Liouville CFT. So it's I think quite interesting. So, but still, this I think this kind of analysis are originally motivated from the static patch, and this our analysis are motivated by more global patch. So, a little bit different, but I think in the end probably leads to the same model. But anyway, this model is also highly non-unitary. So that's and we don't know precisely how to do this exactly about spectrum and so on. So that's really interesting question. Okay, so now I'd like to talk about now go back to entanglement like thing. So this is we can calculate the entanglement entropy in DS3 CFT2. This was first done by Narayan and also Sato, and they find that this entanglement entropy, it becomes complex values. So this is actually, but we want to interpret this complex value as a pseudo entropy. This is a main point of this part. So we have DS3. So boundary, future infinity, we have a two-dimensional sphere. And we talk about subsystem A is some interval here. And we talk about the entanglement between this A and the other complement. So then we can talk about in DS3, so it's like a minimal surface becomes just geodesic length, geodesic line. So we can compute the geodesic length. But here, unfortunately, there are no space-like geodesic which connects these 2 points. This is a future infinity and just pick up 2 points. Even if they are very close to each other, it's impossible to connect by space-like geodesic. Accordingly, if you just calculate geodesic length, uses geodesic length formula, then you end up with a complex value like this. So this, when this angle is theta, so there is a log sine theta times I, because we are picking up time-like geodesic here. And to connect this, we have to go to time-like and then connect along this semisphere. And that gives pi, because it's and this is half of Dojita entropy anyway. So this time-like contribution is like an imaginary value. So it's like t goes to infinity, future infinity. We put some cutoff that gives this contribution. But actually, so we can rewrite this in terms of central charge like this way. So CDS is a real value, so Brown-Weno central charge, and we have to multiply I because central charge becomes imaginary. So we can take this into nice form like this. But of course, we have some imaginary piece. But this imaginary piece is not surprising because the central charge is imaginary in this setup. So if we just trust usual formula, familiar formula, this is just the usual textbook-like formula for entanglement entropy on sphere. So we talk about subsystem A is here, and the angle is theta, and we just get this formula. But we just replace this central charge to be imaginary value, and basically that explains this formula. So that is nice, but at the same time, we have to worry that we talk about the entanglement entropy, but it looks like complex value. It sounds strange. Entanglement entropy always guaranteed to be non-negative. So, but actually, we want to claim that this quantity, this geodesic length, should be understood as not entanglement entropy, but pseudo entropy. So the reason why we claim that is like this. This is because, so we talk about the reduced density matrix. Of course, we have to talk about the reduced density matrix to calculate the entanglement, but this actually turns out to be not Hermitian. So this can be seen from this picture. So we have some boundary of Dojita space is a sphere, and we open some cut along A, and this defines we have some cut boundary condition on lower part and upper part that gives density, reduced density matrix. But we can decompose this into the inner product of these two guys. But upper semisphere and lower semisphere, actually path integral gives different states. Usually this is just Brand-Ket state, but this is different because this in the path integral, even though this is a Euclidean path integral, we have I here. So effective action looks like dual action, but with the central charge is imaginary, so that means we have I. So this path integral gives some phase factor, and phase factor is not simply dual to each other. So that means that this, anyway, what we computed here is not entanglement entropy, but pseudo entropy. So that's the reason why we have imaginary value. So it's quite natural to have that. So, so from that picture, so can we understand what's the reason why we have emergent time direction in DSCFT? So from this picture, Yeah, space-like direction we can understand the entanglement entropy, but in this picture, so time coordinate like this, exactly like this. Time direction is emerges from this imaginary part of this pseudo entropy. That seems to be the relevant thing.
So it is. I have a few questions about the picture in the previous slide. First, there's a state, of course, that one can define on the space-like boundary. There is a wave function one can define on the space-like boundary.
Yeah, okay.
So one might have thought, at least in the absence of gravity, even if that's just a wave function, which is a wave function in a Hilbert space, that one can still define entanglement entropy for the wave function.
Yes, you're right.
Which should be a real number, right? Which shouldn't give you a complex number.
Yeah, but this comes from, this contribution cannot be computed that way because it's like 1 over g Newton quantity.
Yeah.
So I think you're talking about one loop correction, it can be computed to that way.
Well, this wave function in principle captures everything, including gravity. And the second question I had about, the 1 over g Newton contribution was that, there are constraints. So in fact, there's a very severe lack of factorization on the late time surface. Yeah. So there are no local, if you think of operator algebras, there is no algebra associated to A because, there is no operator that's gauge invariant that's localized in the region A. Unlike the case of ADS-CFT, where we have a boundary which is, and you can think of a part of the boundary, and there's an operator algebra that's associated. But here that's not the case. So maybe this is not well defined. How do we know that this is a well-defined quantity to compute?
Okay, but this is only defined in dual CFT. So I'm not talking about what this quantity means in the bulk ds gravity. So if we use this ds-CFT, there is some CFT, Euclidean CFT lives on this S2. And then we can just put twist operator here and define this quantity. That's what
I think in the original proposal by Ramanujan and so on, they were saying, there is some CFT partition function which is equal to the wave function. But now we want to say more. We want to say there's an algebra of operators that we can associate with A, which commutes with an algebra of operators in A complement. But I think it's the constraints just prevent that from happening. The constraints don't allow that to happen.
Yeah, but I think anyway, I'm not sure we can have a nice, simpler algebraic understanding because anyway, this theory is quite non-unitary. So it's not clear how Hilbert spaces, even in the case of type 3 or such algebra, it's not, so it's not clear. But I'm just stick to the Euclidean calculation of just correlation function of twist operator.
We should interpret this minimal surface as an entropy at all. Maybe that's not the right interpretation. I would worry. We can compute the surface, of course, but whether it's legitimate to interpret it as an entropy.
But anyway, we can talk about sphere, right? And then we can conform map to the case with this angle direction looks like time. Then we can talk about time slice and we can define entanglement entropy in Euclidean percentage.
Yeah, but there are still constraints with gravitational patterns.
But I'm talking about just this boundaries.
Yeah, but even on the boundary, the gravity doesn't switch off in de Sitter. Unlike in ADS where the gravity switches off, the constraints are important even on the boundary.
That I'm not sure. Yeah, actually, because if we believe DS-CFT, it's really just CFT degree.
There's a metric.
Yeah, but we fix metric.
Unlike in ADS, where we fix the metric at the boundary.
But the whole wave function, you can fix, just pick up a wave function with a fixed metric. We can just pick up one element of that, right?
Okay.
I'm assuming that.
Okay.
Maybe, yeah, okay. There are many interpretations of DS-CFT. That's really true.
Maybe just as a follow-up to Suvrat's question, can one derive this prescription from something like Lukowitz-Maldacena or something like that? Can you apply Lukowitz-Maldacena here to derive some prescription like this? Or?
Yeah. I think Lukowitz-Maldacena prescription gives some deficit angle here, and then time like it's a bit subtle, but if we some kind of analytical continuation, then you go. I think essentially it's the same derivation.
I see. So assuming replica symmetry is not broken, you say that this is what Lukowitz-Maldacena would give you.
Mm-hmm. Yeah, replica method.
Now I imagine you're thinking of doing the path integral not on the hemisphere. So you use the hemisphere and then you put another hemisphere on top. And then we make a cut, right? And then, so that's how I understand you'd want to do Lukowitz. Yeah. But how do we specify the position of the cut in a gauge invariant way? Because now the whole path integral is a gravitational path integral. And we are trying to say we have a cut and
I'm not thinking this boundary is fluctuating. I'm just putting the Dirichlet boundary condition.
okay, but when we do the full path integral, there's gravity below, there's gravity on top.
Yeah,
So
that's I agree. But I'm talking about the case where just fixed metric.
Okay.
This fixed manifold is dual to some wave function with particular metric in that.
Okay, yeah, fine. I mean, yeah, you should continue, but the metric, of course, is entangled with the other degrees of freedom. So when we fix it, there's some, we get some part of the wave function, which is, yeah, okay, but please
yeah, let's discuss it. Thank you very much. Yeah. Okay, so, yeah, okay, using the rest of time, I'd like to talk about probing digital space from CFT. And here also this non-Hermitian nature of this Hamiltonian and DS dynamics is quite important. So here, what I'd like to do is to probe digital space from CFT, just CFT quantities. So you can imagine some observer in two-dimensional conformal field theory, but how can observer know that actually in the dual description, the observer lives in digital space or anti-digital space. So to probe space-time, we can introduce some local excitation. So then for local excitation, if we have a local excitation, without localization, without any extra degree of freedom, we cannot say how many dimensions we have and so on. We can put some object, then we can move this object in some direction, and then we know how many dimensions we have. So this is basically what we want to do. So we put some local excitation and want to move in time direction or space direction, how many direction we have. Of course, in flat space, we can act some local operator on top of the vacuum, and we can have a time translation and space translation, and we want to do this in digital space. And in ADS case, we can have a very nice story. This is, of course, it's also well known as a HKLL-like prescription, but I'm writing in some state language, basically equivalent. So we have this is a cylinder, and CFT lives on this cylinder. CFT lives on this cylinder, and we excite one point. We can just act on top of vacuum state. We can act some primary state, but this is just a cylinder description. And if we want to see deep inside bulk description, we have to move this point to inside the bulk. How we can do this? So that is a CFT dual of bulk excitation in anti-digital space. And for that, we can use conformal symmetry of ADS3. So we have a SO2, 2 symmetry, SL2R and SL2R, left moving, right moving, and usually in the Virasoro picture, we only talk about the global piece, L0, L plus minus 1, and L0 tilde plus minus 1. It satisfies this condition. And we can act to this operator, even though there are 6 operators, but only 3 operator actually is non-trivial because we have some constraint on this quantum state that 3 generator actually kills that this state. So, but anyway, so we can define this state which sits in the middle of ADS, which depend on rho. So we are talking ADS3, so rho and phi and t, rho phi t. And this state is explicitly constructed by this way. So this is essentially equivalent to HKL, but we rewrite in terms of Virasoro algebra and the so-called Ishibashi state. So this is depend on rho t phi. It's a location in 3-dimensional anti-digital space and dual to, so CFT state dual to localized excitation in the bulk ADS. And so this I is a Ishibashi, something called Ishibashi state, which is like a boundary state. It's sort of boundary state. Ln is a Virasoro and left moving to right moving. But this is only special to n plus minus 1, 0, right? Global Ishibashi state. I. And we have some small time transition that makes this state a cross-cap state rather than boundary state. And then what about the dependence of rho t phi? T is of course Hamiltonian evolution, and phi is a rotation like L0 and L0 tilde, and rho is a non-trivial one, and that actually turns out to be given by this generator. So that way we can move this excitation in the bulk ADS to any points. Okay. So now we would like to go further and to calculate some quantity, which is also useful in digital case. So the basic quantity which we can calculate is 2-point function of this quantum state, x and x prime. So that means we excite this point and this point, and we just take an inner product. And that is should reproduce two-point function in untitled chapter space. That we can completely analytically show this by just taking inner product of these two guys. And that depends on this DADS. This is a geodesic distance between x and x prime given by this. This is a green function of ADS3 or some scalar field with some mass given by this value. And also from here, from this, by appropriating some regularizing this excitation delta with delta, we can calculate something called information metric. So because we want to know how much we can distinguish two different quantum states, which is just given by this breadth metric. And with regularization delta, because two-point function behaves this way, we can easily reproduce the ADS metric. So that means that we can understand this kind of probing space-time like structure. So it's a distinguishability of two different states actually gives distance basically. So that's a nicely reproduced ADS. Okay, so we want to do this in a DS case. So then we encounter many different situations. So, but I mentioned that formal relation between ADS and DS. DS radius becomes imaginary compared with ADS radius. So it's like this. Square of ADS radius is minus DS radius. And we have this correspondence between time coordinate and this space coordinate between this ADS global metric and DS, this static patch metric. Their correspondence correspond to each other by this. And in ADS case, we can talk about, here it's important to think about conjugate property. So L0 dagger is L0, and L plus minus H dagger is equal to minus L minus 1 plus minus. Okay? And so we have this usual BPZ conjugation in CFT, but in a DS case, we encounter very unusual conjugation. So if we can use this, we can rewrite this L0 and L plus minus 1 in terms of killing vector, and we can take conjugation in digital space. Then it turns out that L0 dagger is minus L0 tilde. This means that it's quite unusual. So Hamiltonian now becomes anti-Hermitian. And also L plus minus also something unusual. But this of course satisfies nicely, both satisfy same algebra of Illas algebra. So anyway, so this Hamiltonian is anti-Hermitian. This is a very special property that means we have a non-unitary Euclidean CFT. So even though we have a Euclidean CFT, but this Euclidean CFT is not unitary. So and we think this is the origin of Lorentzian time, where we, in the dual description, why we have Lorentzian time, actually this is highly related to this property. So then anyway, so we want to repeat the same analysis. So we want to probe DS geometry from just starting from conformal field theory calculation. So we find this quantum state is given by this. So this actually, you can take analytical continuation from ADS to DS, basically. So we get this states. So this is a Rishba state part, and we have this time evolution and phi direction. But this T is supposed to be low range. Sorry, T is supposed to be a Euclidean time because we are talking dual theory lives on the future infinity. It's like time direction. It's Euclidean time. But actually, L0 plus L0 tilde is now anti-Hermitian. So that suggests that actually what we thought as a Euclidean time, actually it's a Lorentzian time. It behaves like Lorentzian. That's the new feature compared with ADS case. And this is a radial evolution, theta direction. And this is dual to, so naively we think this is dual to some localized operator, which is dual, localized bulk local excitation, dual to some primal operator in the CFT. However, there is a problem. So if we just take this one, and now we want to do the same thing as in ADS case. So we take an overlap to reproduce two-point function. This we expect something similar in digital space, but this doesn't work at first sight. So this, if we take this state and take its conjugate, just using this conjugate, then it turns out this overlap is just 0. So that means we cannot reproduce green function in digital space. And after some consideration, we find that actually correct answer is likely given by this. Actually, we have to respect some CPT invariance. So there is an example work by Haruo and Numasawa, which claims that all global symmetry in quantum gravity should be gauged, and especially even CPT symmetry should be gauged. And in compact space, obviously, if so, it should be gauged. And we respect that kind of property here. So we start with this one. This is just obtained by analytical continuation from ADS. It's like a local excited state, but we want to take also CPT conjugate of that. We take sum of them so that it's both guys. If we sum of them, it's a CPT invariant. We gauged it. So then actually, it's actually the CPT conjugation in digital space is like antipolar map. It looks like this. And also it flips delta plus minus is given by this kind of two branch, familiar branch in also in ADS-CFT, plus to minus. So then we take this 2-point function with this new basis. This is the old one, this is a new one. And then we can nicely reproduce Dojita green function at the Euclidean vacuum, which is known already before, very nicely. And if by using that, of course, we can also reproduce information metric of Dojita space. Okay. So yeah, okay. So basically, that's what I wanted to.
Sorry, Tadashi, quick question. In the anti-de Sitter case, the Ishibashi state corresponded to having the operator at the center of ADS?
Sorry, Ishibashi state?
Yeah, that was when the operator was at the center of ADS? Like
yes, exactly. Yeah, yes. Rho equals 0 is really center.
Yeah, okay.
And rho equals 0 is exactly Ishibashi state.
Okay, yes, okay. And in the de Sitter context, that the operator is where? It's at the north pole or the south
okay, good. Thank you very much. So Dojita spaces, we have this kind of setup, and so this is theta. So theta equals 0. This theta at theta equals 0.
Thank you.
Okay. So yeah. Okay. So just a summarize conclusion. So we talk about Pseudo entropy, which is a generalization of entanglement entropy. It depends on both the initial state and the final state, and it is generically complex valued. And so if we take difference between Pseudo entropy and entanglement entropy, it measures somehow amount of quantum entanglement in intermediate state, and also it enhances when we have a quantum phase transition between them. So in that sense, maybe can be some new order parameter. And also in the context of ADS-CFT, Pseudo entropy computes the area of minimal surface in Euclidean time-dependent background. And that means maybe we can hold such a Euclidean time-dependent background. So if we want to understand the emergence of spacetime, especially space direction, we have to look at the Pseudo entropy rather than entanglement entropy. And finally, we talked about DS-CFT, and then Pseudo entropy in general becomes complex valued. And from that, we expect some emergence of time direction. Time coordinate is come from this imaginary part of this Pseudo entropy. And there are many future directions, I just mentioned a few. So what's a quantum information meaning of complex value, especially imaginary part of Pseudo entropy is still not completely understood. And maybe more, we can think of more quantum many-body system applications, and what about more implication to quantum gravity. And also, I mentioned also SVD entropy. It's not so easy, but in the end, we want to find some gravity dual of SVD, which is non-trivial because SA is not equal to SV. That means it's not just given by simple geometrical quantity, which localize on the boundary of a subsystem. But it's quite an interesting question. And maybe also these quantities may be useful to constrain quantum field theory by using some inequalities or some property of that. I think I will stop here. Thank you very much.
Thank you, Tadashi. I just wanted to hand over from behalf of ICTS a small memento.
Thank you so much.
For your
Thank you so much.
beautiful lectures.
Thank you.
It's just a ICTS sweatshirt and a mug for you to carry.
Thank you very much. Yes. Great gift. Thank you very much.
For ADS-JT gravity, let us think of a two-sided black hole state, and you create this Hartle-Hawking state. Then it's created on the Poincare disk, lower half of a Poincare disk. Let us say there is matter with some boundary conditions. in the theory, you create that state with respect to this matter. Now you take another state like this, but with the different boundary condition for the matter, and you take the inner product, so you get a disk, right? But there are different states. So this will be like your psi and phi for the pseudo entropy. And in this case, it's a Euclidean spacetime. So the boundary, it seems that it's just 2 points, which are the endpoints of this circle on this tau equals to 0 line. So in this case, could you tell what might be the these extremal surfaces?
I mean, gravity is two-dimensional, right?
Yes.
And
yes,
you have
yes.
a disk and you put
That's right.
different boundary.
Different boundary conditions on upper and lower part.
I see. But still, you can just put 1 point, I think, inside. The
Yes.
horizon point, and you just minimize contribution. I mean, dilaton divided by Newton whole G Newton. So you just minimize it, I think.
All right.
Maybe because it's not symmetric, maybe this point is going down or going up.
I see. Okay.
Any other question? Yeah.
So in the emergence of time, as you described by the entanglement and entropy, so how one can describe the causality in the bulk by the safety story?
Causality.
Causality. I mean, yeah. I mean, some cause and the effect. That relationship.
Sorry, in pseudo entropy.
Sorry.
So, yeah, I mean, sorry, are you talking about Euclidean areas or what's set up?
No. In the bulk, the causal relationship between two events, like something, the bomb blast and someone dead. So that's the causal relationship.
Okay,
So,
but yeah, because we are doing post-selection,
yeah.
right? Causality is somehow not the usual one. Because we have two boundary condition also, space-like boundary condition, infinity.
Okay.
So then, for example, this point is correlated, right? Even though space-like correlated, space-like separated, but because of we are putting boundary condition, space-like boundary condition, these 2 points, usually causally disconnected point is connected. So I mean, it's different structure than usual quantum field theory. Once you do this post-selection.
I see. Okay.
There was one more question.
You mentioned for the de Sitter case, we have a dagger structure like L0 dagger is L0 bar minus L0 bar and L plus minus 1 dagger is equal to L plus minus 1 bar. Do we have a general dagger structure for the other general Virasoro generators? Like say
this one, right?
Yeah.
I think, yeah.
So is Ln dagger is equal to minus 1 to the power n minus 1?
I think it's just probably minus is appears alternatively.
So it's
L2 maybe plus probably.
okay. So Ln dagger is equal to minus 1 to the power n minus 1.
I think so.
Okay.
And then maybe central charge might be
Okay,
imaginary.
Any further questions?
Do we have some notion of first law, second law, or temperature associated to pseudo entropy?
Thank you for the question. But yeah, anyway, in general, it's a complex value. That case we don't know, but I think for holographic case, then I think probably you can find such a, because there is a horizon, then of course this minimal area increases, and it should be, I mean, monotonically increasing. So there, its coefficient you can regard as temperature. Then I think sort of, yeah, first law can be defined. But the second law, maybe you have in mind strong subjectivity. Then I think probably not, strong subjectivity is not true here, because we can easily find a counterexample, and also there are no nice time slices. This is I mean, everything is a space-like direction. There are no causal structure, right? There are no causal diamond. So I mean, you can take this time slice. Also, you can take this is also time slice. This kind of very wavy one, and then very easy to violate strong subjectivity.
And what about temperature?
Temperature, yeah, of course, if you have black hole background, maybe you can imagine some initially high temperature and goes to low temperature. This is obviously two different states, right? And let's calculate this quantity. And I mean, if the later time, you prefer this temperature, and the early time you get up as a temperature. You can consider such as.
Okay, so let's thank Tadashi again for his very nice lectures.